Before I go into the deep details, I would like to thank a couple of my colleagues, Professor Cahill, Professor Crum, and Professor Sasson for fruitful comments, as well as Dr. Jim Connor from the Borough, and my former graduate student, Dr. Tran, and my current graduate student, Katsio Elila Zakultum, who have worked with me really intensively on this research. I also want to acknowledge Dr. Connor, Dr. Huff, and Nicole Swenson, Jim McCormick, and Ron Lovell from the Fairbanks North Park Borough and the Alaska Department of Environmental Conservation for access to observational data that I used for my studies. Furthermore, I couldn't have done these studies without the computational support from the Arctic Region Supercomputing Center and the financial support from the Department of Transportation, the Fairbanks North Star Borough, and the Department of Environmental Conservation. Fairbanks pollution issue is related to PM2.5, as everybody probably knows here. And it's not a new issue. So if you are a long-time Fairbanks, then you probably wonder why 10 years ago you never heard anything about PM2.5. The fact is that in 2006, the Environmental Protection Agency tightened the 24-hour average PM2.0 national ambient air quality standard to 35 microgram per meter cube. In former times, the threshold was 65 microgram per meter cube. If you look at the data that exists for Fairbanks since winter 1990 to recently, you see that this new ambient air quality standard here shown in the orange dashed line has been exceeded frequently in the past in Octobers, in Novembers, in Decembers, Januarys, Februarys, and occasionally also in March. The different lines give different colors, and for the first 5 years I have used symbols because there we only had every third day a measurement. In air quality regulation, people talk about exceedance days when the 24-hour average PM2.5 concentration exceeds the 35 microgram per meter cube. If you see that, we have a large variability about among the years in these exceedances and in the concentration. And this large variability in the concentrations depends on meteorology, it depends on emissions, and on the chemistry. And as you know, the emissions depend on the meteorology, and the chemistry also depends on the meteorology as well as the emission. You get already the idea that we are dealing with a very, very complex system that's highly nonlinear. The measurements I showed before were measurements made at the official monitoring site at the State Office building downtown. And now you might ask the question, how representative is this measurement? Okay, that's probably the point where the air quality is among the worst in the entire Fairbanks. But the question was also raised by various people. So the borough started doing mobile measurements of PM2.5 on a vehicle that drives through Fairbanks on days where we have highly polluted air. This here is an example of such a drive, and you see basically that we have a big hotspot in the downtown area of high concentrations down here in South Fairbanks as well as at the airport. If I would show the one for North Pole, you would see another hotspot in the North Pole area. What are the consequences of the Fairbanks history of having poor air quality in the past with respect to the new standard? In 2009, EPA designated the Fairbanks PM2.5 non-attainment area in response basically to these exceedances. This led to the obligation that a state implementation plan so-called ZIP has to be developed by December 2012. And such a ZIP has to demonstrate that Fairbanks would be able to achieve attainment by December 2014. Well, you can't do that on a dime, so you basically have to do a lot of efforts. So to ensure the compliance, UAF, the Department of Environmental Conservation, Sierra Research Incorporation, that's a company down in Sacramento, California, and the Fairbanks North Star Bureau have worked together to basically assemble information that we need to basically be able to develop such a state implementation plan. The development of a state implementation plan requires to document trends of PM2.5 concentrations, to assemble an emission inventory of PM2.5, as well as every precursors that could lead to the development of PM2.5. It also requires that you gather the current scientific knowledge on what governs the formation of PM2.5 during winter. You will have to gather information or examine the efficiency of emission control measures. You will have to adapt air quality models to be able to quantify the impact of the potential emission control measurements, because you can't experiment with the atmosphere. So you will have to do that in a model. You can think of a model like a wind tunnel or the lab of an atmospheric scientist, and a lot of other things related to getting the information together to come up with a reasonable plan. The State of Alaska Epidemiology group also found that there is a risk for hospitalization when we have increased PM2.5 concentrations in Fairbanks. So that leads us to why we are really concerned about PM2.5. This schematic here shows the size of PM2.5 and compares it to other stuff. PM2.5 is basically particulate matter with a diameter smaller than 2.5 micrometer. That is a 70th of the diameter of a human hair, and I bet you can't see my hair that I hold up here. Okay, these tiny particles get suspended in air, and you breathe them in. Whether you want or not, you just do it. You can't do anything about it. And then they may get stuck in your lung, and they may cause health issues. So that's why we are concerned. The particulate matter is composed of various stuff, and the composition depends on the various sources. In Fairbanks, the PM2.5 is mainly organic components, which can be associated with wood burning, among others. And then we have also a high portion of sulfur particles. The take-home message out of this is that PM2.5 is not a species like ozone or oxygen or CO2. It can be a variety of stuff. It can be organic carbon, it can be sulfur, it can be nitrate, all kind of stuff. So where does the PM2.5 come from? There are direct and indirect sources for PM2.5. And there are natural sources and anthropogenic sources. Natural sources are very fine wind-blown mineral dust that's smaller than 2.5 micrometer. It can be sea salt from sea spray. You know, when the waves tumble over and little droplets go in the atmosphere and the water evaporates, you may have little salt remaining. They can stem from volcanic eruptions. They can be little plant particles that are due to vegetation decay. And they can form naturally in the atmosphere by gas to particle conversion. And that process occurs both in the pristine atmosphere, because the atmosphere is the composition of various gases. So it's even in an unpolluted atmosphere, we have gas-to-particle conversion. And of course, it also happens in the polluted atmosphere. Then you can, of course, get PM2.5 transported into the area, which we call advection. Now let's come to the anthropogenic emissions. There we can have PM2.5 either being directly emitted as the primary PM2.5, or that it forms by gas-to-particle conversion in the atmosphere, basically by a natural process. And other sources are fertilizers, for instance. Now let's look at the sinks. There are physical-chemical processes and chemical reactions that are sinks for PM2.5. Then wet and dry deposition removes the particles from the atmosphere. PM2.5 is, of course, subject to gravity, which basically means that it sediments, but that process is very, very slow. Then, when we have a snowfall event, some of the particles can be scavenged out. They can also be washed out or rained out. And, of course, we can have transport out of the area, and that can be either horizontally or by vertical mixing into higher levels, where it then becomes also subject to long-range transport. Now you are probably curious about that gas-to-particle conversion process that naturally occurs in the atmosphere, and it occurs both in the polluted as well as in the pristine atmosphere. It basically starts out with absorption of solar radiation by trace gases that then photolyze, and that may lead to photochemical reactions that start the process. That may lead to conversion of these trace gases into gases of low volatile vapors, and they can homogeneously nucleate and condensate or some water on it or other gases and build particles, and that way grow. They can also collide then with each other and that way further grow. The other part of gas-to-particle conversion starts out in the chimney itself. There you have relatively high hot vapor, and then these particles condense there, and these primary particles then may collide with each other and coagulate. That means flow together, stick together, and that way they grow. That leads basically to three-modal distribution, and particle of 2.5 micrometer are here. So we have two modes here, the nucleation mode and the accumulation mode. Accumulation refers to that different particles have collided and gotten bigger. And the third one is here, the range 2.5 to 10, that's bigger. So that is more the ones when we have PM2.5 particles swell by water vapor so big that they basically get into the other range, and then we are out of the salad. Okay. The larger particles can also have a variety of sources that I don't want to dig into here anymore. Important for our mitigation interest is that in this nucleation mode here, the smaller one, basically most aerosol particles consist of sulfuric compounds, and so these compounds stem from oxidation of sulfur-containing precursors and to sulfate, and finally condensation into a particle. That basically results into tiny, highly mobile sulfate aerosol particles that then can collide and grow. So the take-home message that you should have gone by so far is that emissions obviously do not go straight into concentration. That means that you cannot say, okay, when I reduce the emission of PM2.5 by 11%, then I will get a decrease in the concentration by 11%. That's not that easy. I wish it would be, but it's not. What's the difference between an emission and a concentration? An emission refers to the release of a gas or a particle into the atmosphere. So an emission is a flow, and flows are basically expressed in terms of a mass per unit area per time. A concentration refers to the amount of substance per unit volume, and is consequently expressed in terms of a mass per unit volume, like microgram per meter cube in the case of PM2.5. How can you visualize that? Okay, let's assume it were allowed in this auditorium to lit a cigarette, which is not. That's why I don't do it. And if I would do this and would blow the smoke into this auditorium, you would get a low concentration of smoke, right? Because it's small. It's a small emission into a big volume. If I would do the same thing, but would blow it into a jar and then close it, then we would have a high concentration in that jar, because that jar is relatively small. So the volume plays a real big role for the concentration, and that's also a reason why we have our problem, because as you will see soon, is that we change our volume in which we emit by having the inversions. Well, let's first keep the thought of where does the PM2.5 come from. Unfortunately, I have to say, Fairbanks air pollution problem is homemade. On the other hand, I also want to say, thanks God, the Fairbanks air pollution problem is homemade. Why I'm happy about that it is homemade is because we do not have to deal with somebody else to clean it up. It's always hard to tell somebody else to change a behavior when they don't have a disadvantage from it, and we have the disadvantage. So when the problem is basically transported to us. That is a big problem in states south of the border, Canadian border, right? So we don't have that problem. Let me see that. Everybody agrees that Denali is from Fairbanks, downwind of Anchorage, right? It's also downwind of the international shipping lane, and it's downwind of anything that would come from Asia. So we can consider the Denali Park as kind of a gateway to Fairbanks. So this here is the pollution, the PM2.5 concentration from 88 to 2011, measured at Denali State Park. This red line that I added to this plot is the National Ambient Air Quality Standard threshold for PM2.5 of 35 microgram per meter cube. You see that it only was at Denali once above that value. And that can be related back to a wildfire. Also the high peaks here, can be related to wildfires. Those that are in winter are usually around or less than 5 microgram per meter cube. Most of the time even less than 2 microgram per meter cube. So what we did is calculate a lot of backward trajectories for those winter cases, and basically for those events where we had these 2 microgram per meter cube or other high concentration in winter at Denali. And when you look at that, usually we can trace that back to the Gobi Desert in lower levels, which basically means that it's mineral dust. Also, when you look at the composition of the PM2.5 during these events, you can see that it's mineral dust and not having the footprint of the pollution in Fairbanks, which has a strong carbon footprint. This here is a movie showing the PM2.5 concentration in colors. The highest value is 10 in purple, this color. And Fairbanks is here where the star is, and where I now am with the mouse. And that's at about 1 kilometer height. What you are looking at here's Asia, and here is the international shipping lane. You see that cyclones pick up PM2.5 and transport it towards the Arctic. But you see the amount that is transported does not exceed 10 microgram per meter cube. So Asia or the international shipping lane may contribute to our problem, but they are not the cause for the problem. The white thing here, the dots here, that are the mountains that stick into that level where I did the plot. And the arrows here give the wind speed and the wind direction. You see, we are here getting a contribution, but not 35 microgram per meter cube. So, what are now the reasons for Fairbanks PM2.5 exceedances? We have to blame the topography, we have to blame the weather, and of course, our own emissions. Fairbanks is located at the edge of a air mass source region. What does that mean? That basically means that air masses remain in place for a long time. That goes along with low wind speed, so the air is just sitting there. And while it's sitting there, due to radiative cooling, that refers to the fact that more energy is lost to space than we receive from the sun, it's cold. So I'm glad I made you laugh. Okay, that basically means the fact that we have cold weather, the heat, and the fact that we have a low wind speed means that the PM2.5 stays in the region. Then we have Fairbanks surrounded by hills on 3 sides, and we also have inversions. That's kind of like a nearly perfect cookpot. You have a lid, and the air can't go anywhere to at least 3 sides. So that means whatever we emit into that volume of air gets trapped and stays there. So we are trapping our emissions and our PM2.5 and the precursor gases that can, due to gas-to-particle conversion, convert to PM2.5. Well, what are the sources? In summer, wildfires, but this talk is not about the wildfires. In winter, the major causes, according to the National Emission Inventory, are heat production, energy production, and traffic. That are our main sources. Okay, we can't do anything about the weather. We can't do anything about the topography. So the only thing that is left to us that we can do something about is the emission. So if we don't do anything, we will not get into compliance. That's that easy. Okay, let's talk about the inversion. What does that actually mean? In the natural situation in the atmosphere, the warm air is on the bottom and the cold air is on the top. So basically, temperature decreases with height. That's good because then the warm air rises, and as it rises, it takes the dirt that's in there, the PM2.5, this precursor, up higher. So it's a cleaning mechanism, right? Okay. Now we have these inversions due to radiative cooling, and also because we have these subsidence due to the high pressure system, because in high pressure system air sinks, and as the air sinks, it warms. And so we get little layers that are warmer than the air below. So that means when we are heating our homes or do anything what a normal human being does, like drive around, produce power, whatever, then we may emit that into this volume that is basically closed up here by the lid of the inversion. So everything that we emit accumulates in that layer. Okay. Can we see inversions? Yes, you can. if you are told how. Look at this here. That's a photo from the Johansen Expressway. You see this brownish lower layer here? That's where we have basically a restricted volume where we get our pollution in and closed. Then here, where I inserted that line, there is another inversion. You can't see that. The only way I know that there is one is if I look at this plume from the power plant. It's going this way here, and there it goes that way. And as a meteorologist, I know this is only possible when we have here a wind shear or an inversion. Here is another one that's on Napa campus, on the West Ridge, the parking lot across the Akazufu building. And this here, what you see here, that is the plume of the UAF power plant as it's creeping along the inversion that I indicated here with that black layer. So, take-home message so far. Normally we have the temperature decreases with height that allows mixing and exchange of air and therefore the transport of the air into the free, polluted air into the free troposphere. If we have an inversion, then the temperature increases with height and that inhibits the mixing and basically the dirty air stays in place, as is schematically shown here. Okay, then you can say, well, it seems to be an impact where the inversion is and where we get the emission. Yes, you are right when you have that. This is a normal situation. Temperature decreases with height. If you have then a stack providing a plume into the atmosphere, it gets really fluffy, going up and down, up and down, up and down, and looks really pretty. And you see also that it's diluting as it gets wider and farther away. Now let's assume you have a surface inversion. That means from the surface onward, temperature increases with height, as shown schematically here in blue. Then you get a plume that's like a pencil. Okay, so you can now distinguish the situation just by looking at the plume. Isn't that exciting? Okay, now assume we have an inversion that's elevated. That means we first have a decrease of temperature with height and then an increase of temperature with height. And we have a stack that emits below that inversion. Then the plume cannot rise unless it's really buoyant through that inversion. And so at the top of the plume, which is the bottom of the inversion layer, it basically is straight like a pencil. While at its bottom, it still has that fluffy behavior. Now let's assume we have an elevated a surface inversion and a stack that is high enough that it reaches and emits into the free atmosphere, basically atop the inversion. You can see that happens when you have more or less the straight part of the plume down here and the more fluffy experience at the top of the plume. So, take-home message, it's really important where the emissions are with respect to the inversion. Okay, so now that we have understood the causes for our air pollution problem, namely our weather, let's go into how we can explore how we can get our problem solved or at least mitigated. One way to do this is to use air quality models. As air quality models basically are able to provide the atmospheric responses, that means the changes in concentration that result in response to emission changes, or just simply the concentration that result in response to emissions. So photochemical models or air quality models permit us basically in the model world to easily change the emissions, cost efficient, because you don't have anything and you can dream up whatever scenario you want. And So these photochemical models allow us to assess, on one hand side, the contribution of emission source to the PM2.5 concentration at breathing levels. And you could answer questions like, what do the power plants contribute to the PM2.5 concentrations at breathing level? They also allow us to answer so-called what-if questions. So like, what happens to the PM2.5 concentrations at breathing level when we change out a certain number of non-certified wood-burning devices with EPA-certified ones? Or what happens when we reduce the sulfur content in fuel used in oil-fired furnaces and oil-fired facilities? Or questions, what happens if we do this and this together? You get the idea. Okay. So once we have run these models, how do we, with that, really assess the future air quality in response to emission control measure? It's a really complex mathematical process. It's probably difficult, really difficult. But let me just line out the idea. So simply speaking, you basically calculate a so-called design value based on 5 years of observation at the official monitoring site. The official monitoring site in Fairbanks is at the State Office building. And you calculate that design value for the base year. For the Fairbanks zip, the base year is 2008. And if you do this complex calculation, you get a value of 44.7 microgram per meter cube. Then you adapt a photochemical air quality model for Fairbanks. And you run the model for the base year with the emissions as they had been in the base year. And then you run the model with the emissions that would represent the emissions of your control measure. And then you calculate the relative response factors for the various compounds of the PM2.5. And that's basically the ratio of the concentration from the projection to the ratio of the concentration that you get with the run with the base year. Then you apply these component-specific relative response factors to the observation to basically calculate the PM2.5 estimate for the future year. And this PM2.5 estimate you compare to the National Ambient Air Quality Standard value, which currently is 35 microgram per meter cube. So if your future value is smaller than the 35 microgram per meter cube, you are out of the salad and the test is passed. If you are higher than that value, well, you go back here, try another measure. Right? Okay. Let me quickly give you the methodology and the experimental design for the simulation that I did. I used the Alaska adapted WRF-Chem. Note that WRF-Chem is a research model. It's not the EPA regulatory model. And the Alaska adaptation basically includes things like Alaska-specific background concentration. Our background concentration are better than those in the lower 48. Cold region dry deposition because we have a closed snow cover for at least 6 months a year. And of course, we have a snow cover for 6 months a year, so we have to adapt the model for that. Then the model comes without Fairbanks or villages or Anchorage to exist, so we basically used satellite data to put Fairbanks in place and other minor tweaks of the model to basically represent Alaska condition. Then you use the Alaska emission allocation model. And the simulations that I show for the investigation on point source contribution, I use the National Emission Inventory of 2005 and performed simulation for winter 2005-06. And for the other scenarios that I did, I used the National Emission Inventory of 2008 and did the winter 2008-09. And I will present here results of PM2.5 responses to different emission scenarios, like various wood-burning device change-out, a gas scenario, scenario where we assume introduction of low-sulfur fuel, and a combined measure where wood stove devices are changed out and we introduce low-sulfur fuel. This here is the model domain, so that you can orientate yourself when you look at the results later. Fairbanks is in the middle, so that's easy. Just cross it like that, and there's Fairbanks. This here is the population density. You need that for allocation of the emissions. This here gives you an idea where the streets are, basically where you would have the traffic emissions. And this here, once more, shows the topography and illustrates that Fairbanks actually is enclosed by by mountains from 3 sides. So let's start with the investigation on the contribution of point sources. That is basically based on a WRF-CHEM simulation with all sources switched on, including also area sources, your households and everything. And one simulation where everything is switched on except the point sources, these emissions are excluded. This is, of course, an unrealistic scenario, but in the model world, you can do that. And it allows us to assess the contribution of the point sources. The idea behind that is if we switch them totally off and it doesn't help, then adding filter will only help a little bit, but it would not bring us into compliance either. Okay. First, I have to define for you what is a point source. A point source is everything that has a stuck in the wind. And basically, all point sources have to be permitted. That means they are the best known emission sources in the entire game. Area sources are all the houses, it's agriculture, it's a fuel station. And then we have also on-road traffic that are basically line sources. In the model, we of course consider that when we have a point source, that it emits at higher levels. So it's considered in the model that it goes into higher model layers. While when you have a house or a car, it's emitting into lower levels. This plot here shows the day of the month here and the PM2.5 concentration on the y-axis. Here the dotted line in orange is again the National Ambient Air Quality Standard of 35 microgram per meter cube. And REF stands for our base case, reference run, and NPE stands for no point emissions. The numbers behind this indicate the months, like 11 for November, 02 for February, 12 for December, and 01 for January. If you look at this, you see that among these months, there is a high variability. And you also see that the differences between the simulation with the point sources switched on and that with the point sources switched out are relatively small. On average, it's only 1 microgram per meter cube that you have more on average over the entire non-enchainment area and the 4 months here simulated due to the point sources. So that means that inserting filters will not solve the problem. But as you see on 4 days, circled here, having had the filters, we would not have had an exceedance. So it will help, but it will not solve the problem entirely. This here is a zoom in onto the Fairbanks. This polygon is the non-enchainment area. These little columns indicate the major point sources, and these circles indicate where we have exceedances in that grid cell. The upper part of the plot here is from the simulation with all emissions, and this here is from the simulation with no point source emissions. And you see that basically, due to the point sources, we have in these 3 grid cells here an exceedance where we wouldn't have one if they won't exist. But you see that without the point sources, we already get exceedances, which basically tells us that we have to examine whether reducing the area or traffic emissions may be an option to basically clean that up. Okay, I said that the point sources emit into higher levels than the area sources. And so we wanted to look at where does a point source really impact the concentration at the breathing level. So what we calculated was the correlation between the emission into the level where the emission goes and the concentration at the surface at various distances from the point source, and the point source is here. So if we do that, we see 2 things. The highest correlation, meaning the highest impact, is about 4 to 6 kilometers away from the point sources, from the point source. And we also see that the higher we emit, the lower the correlation is. That means we have a lower impact. Unfortunately, we have in the far field or near field some other point sources for this one here. So that is the reason why here the correlation goes up. It's basically the response to these guys down here. Okay, this is just one example. The other point sources show a similar behavior but with lower correlation. Of course, if you have done some statistics, you see that the correlations are relatively low. However, we tested them for statistical significance, and they are 95% significant. We have a 95% confidence level. That basically means that we are 95% sure that that correlation is due and actual. You might have to do such tests because sometimes you could have correlation just by accident, like the decrease in birth rate and the decrease in the rate of stocks, right? That correlates, but there's no relationship. And if you look at this, there is. Okay. So what's the relative response to switching off point sources? Remember, we can't do that, but also remember the relative response rate was the concentration future or projected over the one that is the base year. This is shown here, and you see that in the Fairbanks non-attainment area, mostly the outdoors benefit. If you think about the ratio, 1 would mean no change. Everything that's lower than 1 would mean we have reduction of the concentration, so that would be a benefit. So the lower the value is, the relative response factor, the bigger is the response. And if it's greater than 1, then that would mean it's counterproductive. It's making the case worse. Okay, if you look at the absolute concentrations change, the difference, over the entire 4 months, then we see that we have on average in this area about between less than 4 microgram per meter cube less. So the actual difference is relatively small. If we now look at the investigation of the wood burning device change out, these are again Wolfram simulations using the emissions of 2008-09, and we investigated various wood burning device change out assumptions. The difficulties with this study is that we have relatively few knowledge about the number of wood burning devices that are out there and the locations. And Also, there is only limited knowledge about the wood burning behavior, the frequency, the journal course, when is the wood stove fed, and stuff like that. And also among the share of multiple heating devices in a house. How do you share the heating between your oil furnace and the wood stove and stuff like that? Also, as you probably know from TV, if you burn wet wood, you get different emissions than if you burn dry wood, and therefore it's recommended to do dry wood, but there are uncertainties related to that. This here are the emission rates of the various wood stove burning devices. You can find them in the report of Dr. Davis and co-worker from the Cold Climate Housing Region Center. And you see that the non-certified devices burn dirtier than the certified ones, and that the wood boilers are the dirtiest there are. For a weak wood stove change-out program, assuming a 4% emission decrease and a relative leads to basically a relative response in the concentration of about 5% on average over the entire winter and the non-attainment area. Here we see the differences, and you see that here the maximum differences are less than 3 microgram per meter cube over that period. And if you look at the relative response factors, you see that in the non-attainment area you have a heterogeneous behavior, but you also see that you are far away from really low values. It's kind of between 1 and 10%. So between 1 and 0.9, which means between 1 and 10% reduction. If we now have a rigorous wood stove scenario, and we did a test for that with, for 15 days, and that's a scenario that assumes the numbers given in Davis et al. The other scenario has numbers that were given in Charleston et al. That are based on a survey that was made in 2010. If we use the numbers in Davis et al., which are the numbers that the borough gave them as their estimate, we see that we get a strong response, and we would have good chances to clean up if that number of wood stoves that was estimated to exist to be non-certified wood stoves would really be all switched off. And as you see here, we get over large areas of the non-attainment area reductions in the average over the entire half a year of 5 microgram per meter cube. Not entire year, for 15 days, sorry. This here is a comparison of the reference run and the weak wood stove scenario, and you see that in the temporal evolution, that reduction does sometimes lead to getting it under the magic line, but most of the time it does not. Here it compares the various scenarios that we did with assuming other numbers of non-certified wood stoves. And you see from this that the success of a change-out program depends on how many of the non-certified wood stove exist out there and can be replaced. Then another scenario that we did with respect to wood stove is that we assumed that people voluntarily do not burn wood. And the fact is that in 2008, there were 26 days with exceedances. And the other fact is that there exists no real-time air quality forecast model for the Fairbanks area. That means we cannot use a forecast model to basically say, well, tomorrow we will have an exceedance. So you basically have to derive that or relate it to other facts. And if you want to basically ask people for non-burning wood, you have to make a decision when you will ask for that. Let's assume we would ask for not burning wood when the PM2.5 concentration exceeds 30 microgram per meter cube on a day. If you look at the 2008 data, then we would have had 34 alerts in that 6 months. That's more than a month where you would be asked to not burn wood. And if you now look at the concentrations on the next day, 5 of these 35 alerts would have had concentration below 35 microgram per meter cube on themselves. So they would have been false alarms. Okay, nevertheless, let's do that scenario. And if we do that for the entire winter, assuming that people do not burn any wood when the day before we had a concentration greater than 30 microgram per meter cube, we would get relative response factors that are very close to 1 that I can't even plot because I would end up with a totally red plot. And I think you already see red. That's why we are in black. Okay. So what I plotted here is basically only the relative response factor for that for 34 days with voluntary non-wood burning. And you see that, oh my gosh, that's getting even higher than 1, which she said before, is that it's getting worse. Why is that? Well, when you change one device against another one, then you do not only change the emissions of PM2.5, but you also change the emissions of the precursors. And you learn that the precursors are important prerequisites to basically build particles in the atmosphere, so-called secondary particles, by gas-to-particle conversion. So we changed that way the composition of the atmosphere and the food for gas-to-particle conversion. And this simulation does not even consider that when you have a heating system that's independent of each other, that means the wood stove would not heat the water of your system, that you would have first to heat all that water in the system with your furnace, which takes a lot of energy and causes a lot of emissions, right? So that's not even included in this simulation. Okay. Now let's try another experiment with the wood stove. Let's assume we could exchange all wood stoves in the non-enchainment area by gas, by natural gas. Okay, in the model world, I said you can do that easily, so I did. And so the reference run, again, the 2008-09 emissions, and the experiment is basically 2008-09 emission for everything as it was, except for that I take out the wood burning and replace it with gas. But what you have heard already, there is one issue with gas. It releases also a lot of water vapor into the atmosphere. So I consider that too. So if I do that, the average PM2.5 emissions and the concentration reduction is 11% and 13% respectively in the non-enchainment area. Okay. If we now have the gas instead of wood burning, that may reduce the PM2.5 concentrations locally more than 20% on average over that entire winter, as you see here. And the differences here are relatively low on average over the winter, but they are pretty constant. I said, well, you get also a lot of water emitted, and that basically is the prerequisite for ice fog. And here I plotted the number of days with fog in colors here, number of days. And you see here in the scenario with the gas a long basically the highway between Fairbanks and North Pole, you get a couple of more ice fog days. That's not fun. Okay. I tortured you with the gas to particle conversion, and as you recall, I said that SO2 is important, and that a lot of that nucleation mode is some sulfur components. So the idea behind that's important because the idea behind a so-called indirect measure is that you reduce the SO2 so that you reduce the gas to particle conversion and that you get less PM2.5. That is like having a fat dog, you feed the dog less and hope that the dog gets slim. Okay. Again, simulation with the reference, for the reference run, same, normal emissions. And then the experiment assumes that the oil-fired furnaces and facilities use low-sulfur fuel. That does not only change the emissions of SO2, but also the emissions of PM2.5 as well as other precursor gases. But the major emission reduction is the SO2. Okay. Here, you know already this kind of plot, the day of the months here, the 24-hour average concentration here, the reference run, and the low-sulfur fuel run in dashed. And at the end, we have the respective months, October, January, November, whatever. If you look at this, you see again a high variability among the months, but in contrast to the plot that you looked at before, you see that the differences kind of vary really strongly between the two lines. And sometimes it even increases. And what is it? Gas to particle conversion. Okay, so this here are the concentration at the grid cell for the official monitoring site. And if I would show you other grid cells, they are having kind of a similar behavior. So here, again, the absolute differences, relatively small on average over that half a year. And here, the relative response factors. It's really heterogeneous over the entire non-enchainment area. That means some neighborhoods benefit more than others. And you see also that the most benefit, the lowest values here, remember the biggest benefit you have and you have the values the lowest, is way out of the non-enchainment area. So why is that? Well, it's an indirect measure that relies on gas to particle conversion. And the gas to particle conversion, of course, requires some time. So you get the biggest benefit out in the woods. I forgot to say that on average over the winter, the 6 months, you get kind of a similar response of about 5 to 6%. But temporally, as you have seen before, you have a high variability. That means that measure is not very stable. So, no non-enchainment area so far did a multiple emission control measure. That basically puts us into new land and exciting research. We can have to investigate what if we reduce, for instance, the sulfur content in oil-fired furnaces and oil-burning facility, would exchange wood, non-certified wood stoves at the same time. What would that bring? That also leads to the question, can we estimate the impact that this combined measure had by the sum of the impacts of the single measures, right? Like, whoops, what's going on here? Okay. So, if we now answer the first question, what does the combined measure bring? This is, again, simulation before, reference simulation, and again, the simulation where we basically exchange wood stoves that are non-certified. At the same time, we also assume that we burn low-sulfur fuel in the oil-fired furnaces and power plants. Here we see the absolute differences, and you see that that's again very heterogeneous over the non-enchainment area. And here are the relative response factors. And that's really heterogeneous who benefits most, and kind of provides a similar picture as we had for the low-sulfur fuel before. Well, because it involves an active, an indirect, and a direct measure. So again, the greatest benefit outside the non-enchainment area. But we see that we are closer to the reduction that we want to see. So the second question is, could we assess by knowing measure A produces that, and measure B provides that benefit, if we combine these measures, the sum of the benefits of A and B. Okay? So basically that means if we have a change due to the wood stove change out, and add that change to the change that we get due to introducing of low sulfur fuel, would that then be the change that we would get when we do it both at the same time? Would be good because we save then a lot of simulations and a lot of assessment, right? Well, for me it's good, it's not, but let's lead you through this. So, a little bit high school math. If you now throw subtract on both sides the change of the mixed measure, then you get 0 here on this side, and you have delta WSR plus delta LSF minus delta mix, or you do it the other way around, that you throw this, subtract that from there, and you get to this equation. Okay, if the sum would be equal to the combined measure, then you get the 0. And then they would actually superpose, and you could assess the mixed measure by the changes that you can expect from the single measures. If that leads to a value that's greater than 0, then it's exciting, because that would mean that if you have both measures at the same time, they would trigger each other to an improvement. If this difference is smaller, then that's not so exciting, because that would mean that these two measures would basically fight each other and would lead to a smaller reduction than the sum of the two. Okay, so the plots that you look at in the following are basically this alpha, basically this here. So if it's greater than 0, okay, you can see that. If it's greater than 0, then that means it triggers and enhances the response. And if it's 0, so like yellow and green here, that's around 0, then you can assess it with the sum. And if it's smaller than 0, then it's fighting each other. If you look at October, we see that that's greater than 0, which basically means that it triggers to a higher response. This is good, right? You want a higher response. If you look at November, it's kind of the sum. This is good too, because we could say, okay, for November, we can assess the impact by the sum of the single measures. Now let's go through the other months. If you look at December and January, we could also say, okay, the sum is a good assessment for what the combined measure would bring. If you look at February, it's not, and it's a decrease. And if we look at March, we could assess it again. So what is different between October, November, and January, February, December would be in the same category as November. And what's different from that for February and March? Well, in October, we still have a lot of daylight. And in February, we again have a lot of daylight. And as I said, gas-to-particle conversion requires photolysis as a prerequisite for building the precursors. Okay, now you can argue, well, March we get already the days longer than the nights. So why does that not function for March, sorry. Well, if I look at the meteorology for March, that is the month where it is more windy, which basically means, as we learned at the very beginning, that the stuff is transported out of the area and we have a lot of mixing. So basically, we do have better cleaning mechanism. So obviously, adding up all the changes seems not to work for months with more daylight, like October and February, unless there is a lot of wind. Okay. Before I finish and let you ask questions, let me summarize the conclusions that we got out of this study. The 24-hour average PM2.5 concentrations have the same hotspots for the various scenarios. So the hotspots remain the same. But most of the time, they have decreased concentrations. So all the measures except the voluntary non-wood burning basically lead to a mitigation of the problem. However, they do not lead to attainment. All investigated emission control measures except that voluntary non-wood burning mitigate the concentrations. The major findings are that the success of any change-out program depends on the actual number of wood stoves that can be changed out and the number that exists. And unfortunately, there is not much knowledge on the wood stove behavior and on the number and where they are and so on. The introduction of low-sulfur fuel or cleaning up of point sources, remember we can't switch them off, is most beneficial outside of the non-attainment area. With respect to the point sources, it's because they emit at higher levels. It takes time to get down to the breathing level. And with respect to the low sulfur fuel, it takes some time till the particles form. If we introduce natural gas at basically the cost of wood burning in the non-attainment area, we will get more ice fog days. We also see that switching wood to gas burning would basically provide the most stable reduction. If we do the multiple emission control measure that consists of low sulfur fuel and change out of wood stoves, we get the farthest in the right direction. And we also see that the more a control measure relies on precursor reduction, that it becomes much more sensitive to the meteorological conditions. That means it makes it less predictable what will happen because it depends on the meteorology. This is due to nonlinear processes that the efficiency of a multiple emission control measure cannot assessed by basically the sum of the single measures. So that means we have to do investigations for any multiple emission control measure that we want to think about. And these nonlinear processes, we found that they are least important when we have low insulation and when we have good mixing. And now That's all I have for now.